Hello, welcome. In this video, we're going to be looking at the ellipse, the amazing ellipse. And I say that only because every time I look at it, I feel like there's something else to discover. For example, in all of my work with the ellipse, I did not come across the trammel of Archimedes until I saw it in person. So that is interesting to me. There is a way to think of the ellipse in terms of these points sliding along two lines. What else can we discover? Let's first talk about the fact that the word ellipse doesn't mean oval. The root of the word ellipse connects to the word, or phrase, I should say, to fall short. To fall short of what? Well, this falling short has to do with the cone. And in this little classic wooden model, you can see that these cuts along the wooden cone, each cut at a different angle gives us a different conic. So right here, one of these cuts is a parabola, one of them is an ellipse, and one of them could be the start of a hyperbola, depending on the angle of the cut. Here's what I mean. Let's take a look. So I'm going to make this larger. So this is in GeoGebra, and this shows you this plane right here at different angles to this double napped cone. There's the top part and the bottom part here. And what we're trying to highlight is that as the plane is crossing the double napped cone at different angles, the intersection of the plane and the double napped cone gives you different conics. So let's pause it and explore it together. You can see right here, kind of turn this around at different angles. Right now, the plane is intersecting the bottom half of our double napped cone at a circle. And in fact, if I drag this angle like this, you can see the circle begins to change into a more recognizable ellipse, right? The ellipse is a more eccentric circle. It's kind of drawn out like an oval. You can see it here. There's our ellipse, right? And yes, it's true that a circle is a type of an ellipse. But let's focus on the fact that this ellipse right here, the angle of it, look at the angle of this ellipse in comparison to the base of the cone. So this angle right here, that angle is less than, it falls below the angle of the cone right here. Right? The angle of the cone, if I kind of look at it from this perspective, this triangle angle, that angle right there is larger than the angle of the plane intersecting with the base here. And that is where we find ourselves getting an ellipse, whenever that angle is less than the angle of a cone. So in all of these cases here, right, we have circle, which is a type of ellipse. It stays as an ellipse. Even now, it looks like a parabola maybe, but that's not. It only is cut off here because of the way we're viewing it in our window. If we zoom out a little bit, there you can see it's still an ellipse. It remains an ellipse until the angle of intersection is equal, there it is, to the angle of the cone here, this base at the cone. You see that angle is now matched here? That's when we get the parabola. As soon as I go under that angle, as soon as I do it, we're right back to an ellipse. And again, I can just zoom out. There it is, there's the ellipse. So if I want to get the parabola, I make sure the angles are matching. There it is. And then the hyperbola is just over that angle. That's where the hyperbola starts to form, where the angle of intersection between this plane right here and our base is a steeper angle than the angle here in our in our cone right here. Two-dimensionally, you can see it as a triangle. You can see that this is a steeper angle than this angle here, and that's the hyperbola. So the double napped cone and the fact that we're studying conics helps us understand the root of these words and many other things as well. Let's go back here. Okay, so let's look at this from a different perspective, the two-focus definition. So the definition says that this elliptical shape right here has an interesting property. It's a collection of points such that the sum of both radii is constant. So if you have a focus point at A and a focus point at B, it's like having two centers to your ellipse. The radius from A to a point on the ellipse and the radius from B to that same point could be different, but the sum of them is constant. It has to be. So if we have two foci, add up both radii, you always get the constant number, which I call the sum, or SFR, the sum of the focal radii. Now, we'll talk about why this is in a moment, but this also fits really nicely into the locus definition, locus, which is a collection of points, for the parabola and circle, and also the hyperbola. The parabola is a collection of points equidistant from a central point and a line. A circle is a collection of points equidistant from one center. But now that we have two centers, we have a collection of points that's equidistant from the sum of the radii from both centers. So put the radii together and you get a constant. So it's kind of like a circle, right? Except with two radii, you put them together and you get a constant. Interestingly, you'll see soon that the hyperbola has a constant as well, but it's when you subtract the radii. So we'll talk more about that. So this is a fact that defines the ellipse. Why does this make sense? Let's look at it from two perspectives. The first perspective will draw this out. Let's see if this loads. There it goes. So if you were to draw an ellipse, like here's two focal points, F1 and F2. This right here, these two lines represent a string pulled back by a pencil. And here's where the pencil is. If you were to tie this string to, let's say, these two tacks or focal points, the string's length would be fixed. So this radius, this part of the string, plus this part of the string here is constant. The string is never changing, right? And the location at which you put the pencil breaks that string into two radii. Put them together, you're always going to get the same string. What's amazing is that if you drag this around, if you do this, and I encourage you to do it, it's really nice to have a physical association with the ellipse. If you do it, you get an ellipse. It's really cool. So you drag it around, the string's always the same, so the sum of the focal radii is constant, and you're always going to get an ellipse when you do this. Okay, that's the first observation to make. Another observation to make, I think, is captured nicely here. Let's make it a little bit larger. So in this animation right here, we start to get some more terminology for the ellipse. The two vertices here are the endpoints of the major axis, the longer axis of the ellipse, where it meets the conic, right? So these are the two vertices here. As you might guess, the other axis is the minor axis, and those points are called the co-vertices. So we have the vertices on the major axis, co-vertices on the minor, and the minor axis is shorter than the major axis. Now, as we drag these points around, you can see the two radii from both focal points changing. But if you drag it to a vertex, you could probably imagine, oh, look at that. If I put the two radii together, it's constant because, again, you could think of it as representing a string, but also, because if you put those two radii together, you get the entire major axis, and that's a key observation. Imagine this red piece if I was just to put it on this side, right? The distance between the focal point 1 and this vertex is the same as the distance from this focal point and this vertex. So I can just take this red piece and fit it on this side, and I think if I slide this, it'll work. Kind of a way to do that, right? There they are. The two radii put together has to be the major axis. It's an incredibly useful aspect of the ellipse. And this is true anywhere, actually. It's not so obvious everywhere. But here, for example, those two pieces fit nicely still as the major axis. Anywhere you go on the ellipse, put the two radii together, you get a constant, and you also get the major axis. Now imagine I'm right on the minor axis, so right above the center of the ellipse. You can see in this case, it's an interesting observation, that these pieces are now precisely the major radius. It's kind of an estimate here, right? But if you can see that if I slide those pieces over, if you're in the right spot, those radii, those lengths will be the major radius, which is half the major axis. So if you've got a point that's precisely on the minor axis at the covertex right here, that length is the major radius. As you might guess, there are some right triangles here that we can use to our advantage. Let's take a look. Okay, so summing it up, we've got the SFR, add the radii together, you get the major axis. And as you might have noticed, we have this relationship, which we can use to our advantage. The radius you saw, here's the covertex right here. That distance from this point, which is a focus, up to the covertex, right, was exactly half of the major axis. So the hypotenuse of a triangle right here could represent the major radius. If this leg is the focal distance, that's the distance from the center of the ellipse to a focal point, and this leg is the distance from the center to the covertex, which we call it's half the minor axis, it's the minor radius. And that's the relationship we need. I encourage you not to think in terms of A's and B's and C's here. And many books will do that. It works for some students. If it works for you, great. But instead of A's and B's and C's, I think about what legs I have in my triangle and how it's going to help me. The focal distance squared plus the minor radius squared will give me the major radius squared. Let's try this out. So in this example, notice we had to sketch it, find the sum of the focal radii, and find the coordinates of the focal points. So let's do that. Okay, so I've started this out, and I'm using a PowerPoint here, so I'm not going to draw it by hand. I don't have my tablet with me. But the first thing I would do by hand is mark the center. So try that out. Mark 3, 2. Then these denominators become really useful. Let me just tell you what to do, and then we'll review why this makes sense. So the larger denominator, 36, corresponds to the major axis. And you can see I've already drawn the ellipse, but the idea is that the major axis of the ellipse is twice the square root of this number. So the square root of 36 is 6. And if I double that, I get 12. That is the height, in this case, of the major axis. And the major axis, again, just corresponds to the bigger number. So in this case, I go up 6 and down 6 to get my two vertices. And then I go left and right by twice, well, I go left by the square root of 20 and right by the square root of 20, right? It's the square root of that number. You can see the square root of 20 is between 4 and 5, right? 4 squared is 16, 5 squared is 25. So I go a little bit more than 4 to the right and a little bit more than 4 to the left to get the co-vertices. And the minor axis is just twice the square root of 20. If I was drawing this by hand, which I want you to be able to do, I would use that information to draw a rectangle. I tend to draw rectangles and then fit the ellipse inside. So I know the major axis is 12 and the minor axis is twice the square root of 20, which is a little bit bigger than about 10, right? Because again, between 4 and 5 in both directions. So, sorry, a little bit smaller than 10 in both directions. So I draw a rectangle with a width a little bit below 10 and a height exactly at 12. So I should see rectangles being drawn, and then you would label the approximate location of the co-vertices and vertices, and then draw the ellipse inside that rectangle. All right. Next, we've got to find the focal points. Well, this major radius 6 right here is the hypotenuse of this triangle. This distance right here, this minor radius, is the square root of 20. We know the major radius is 6. We can calculate the focal length by using the Pythagorean theorem. 36 minus 20 is 16. Take the square root, it's 4. The focal distance from the center up to a focal point is 4. And we go up and down by 4 to find the two focal points, and we're finished. So to kind of recap, you see an equation like this. The large denominator is the major axis. The smaller, so let me say it a different way. The larger denominator can be used to find the major axis. The smaller to find the minor axis. And the major and minor axes are twice the square roots of these numbers. Find those square roots, double them, and then draw your rectangle, height and width. Approximate, because you know where the center is, approximate where the co-vertices are and the vertices, and then draw that ellipse inside the rectangle. Finally, use what you know about this triangle to solve the missing pieces. In our case, we knew the major radius, we knew the minor radius, so we used that in the Pythagorean theorem to find the focal distance. We want to tie this into circles. Circles are a type of ellipse. The circle equation right here, if I divide everything by r squared, I would get this. Notice this looks exactly like the equation of the ellipse. And it essentially is, except with the ellipse, you can have two different radii. So we use a's and b's. What I'm saying again about this number is that you're seeing a squared, right? So if you want to know what the x radius is, and it could be minor or major, take the square root of this and you'll have it. Double it and you have one of the axes. Do the same here. Also, again, the ellipse has a constant sum of focal radii, so how convenient for us that there's a plus in our equation. It helps us remember that. Let's do one more example. This time we're given the focal points, and we're given the sum of the focal radii. We want the equation and a sketch. So the first thing I would do is graph the two given focal points. Here they are, -7, 5 and -1, 5. The center is exactly halfway between. You can count or just average your x values. So our center is at -4, 5. And I drew this line as a length of 10 because that's our major axis. The sum of the focal radii is the major axis, which is 10. So we have that information. We now set up our triangle. In our case, we know the distance from the center to the focal point we can count is 1, 2, 3. We also know that this hypotenuse has an exact length of 5 because that is the minor radius from the center, 5 over to this vertex right here. So we have our major radius of 5. We have our focal distance of 3. The minor radius is 4. And then we can use that to set up our equation. In this case, our center is at -4, 5. So there's our values, 4 and -5. I think I said that backwards. The center is at -4, +5. So we put a +4 and -5. These are opposite of the values you see here in this point. We have a 25 in this case. Again, that's just the major radius squared, and then the minor radius squared is right here. Finally, I would draw your rectangle. You kind of have it set up here already. You see that rectangle? And I didn't label it in this image, but your vertices and your co-vertices, mark them and then draw the ellipse inside the rectangle. Also, with parametrics, as you might be familiar with, the equation of a circle is just the radius of the circle times cosine of t plus h and plus k for a center hk. The ellipse is the exact same. How cool is this? Except you have two different radii. So there is your A and B with your center h and k. All right, I hope this helped.